Pluto is a mysterious distant dwarf planet that was once part of our solar system's planetary group. But a recent surprising announcement by leading astrophysicists Neil deGrasse Tyson and Michio Kaku has put Pluto back in the spotlight with a shocking discovery. They suggest that the icy world is on a possible collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there more to the impending cosmic collision? Join us as we explore the possibility of a Pluto-Neptune collision. Pluto, a former planet, has been demoted to a dwarf planet due in part to its unusual orbit, but it remains a subject of fascination and study in the astronomical community. Recent predictions by leading scientists place Pluto's orbit dangerously close to that of Neptune. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising red flags about the possibility of a dangerous collision between the two planets that could pose a major threat to Earth. How could such an event be possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a whopping 248 years to complete one revolution, meaning that since its discovery in 1930, it has not yet completed a full revolution. But the intrigue doesn't end there. Pluto's path is shown as being very elliptical, a significant departure from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is that it is tilted 17 degrees to the plane of the ecliptic. Pluto's path is much steeper than that of the other planets. This inclination and elliptical nature adds complexity to its orbital pattern. One of the most interesting aspects of Pluto's orbit is its intersection with Neptune's path. During each orbit, for about 20 years, Pluto actually moves closer to the Sun than Neptune, defying what one might expect from Pluto's position in the solar system. This leads to a natural question. Why didn't Pluto collide with Neptune? The answer lies in the gravitational influence of other planets. The study of Pluto's orbit began shortly after its discovery. At first, astronomers tried to understand its unique trajectory. Unlike other planets whose orbits are relatively close to the ecliptic, Pluto's orbit stands out because of its steep inclination and elliptical shape. The mystery deepened when it was discovered that Pluto's orbit actually intersects with Neptune's orbit. Even in this complexity, the stability of Pluto's orbit demonstrates the complexity of cosmological dynamics. The three-body challenge in space is about figuring out how three objects in space, Pluto, Neptune, and the Sun, move and interact with each other under gravity. It's like trying to predict where they'll go based on where they started and how they're attracted to each other. In the case of Pluto, this problem shows how Pluto's path, Neptune's path, and the Sun's gravity work together in complex ways. The terms azimuth oscillation, latitude oscillation, and VZK oscillation are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is azimuth oscillation. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is at least 90 degrees from Neptune. This spatial separation is important to prevent collisions. Latitudinal oscillation, on the other hand, refers to the vertical movement of a celestial body along its orbit. In the case of Pluto, this means that when it approaches Neptune or another giant planet, it is well above its orbital plane, providing an extra layer of protection from potential collisions. Another important component of this equation is the VZK fluctuation. It is named after three scientists, von Zeipel, Kozai, and Lidov, who studied how things move in space. It is about how three space objects, Pluto, Neptune, and the Sun, are attracted to each other by gravity. This attraction affects the way they move. In the case of Pluto, the VZK helps us understand why its path around the Sun is so unusual. Even though Pluto's path may seem irregular, this wobble helps Pluto move smoothly over long periods of time. The VZK fluctuations show that even though things in the universe seem rough and random, there are some patterns and rules that keep everything in order. All of these components keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or deviate from its course. This three-body problem helps us understand how these paths change due to the way these cosmic objects attract each other. Studying this can help us learn more about Pluto, our solar system, distant worlds, and their stars. Numerical simulations from the late 1980s showed that despite these stable properties, Pluto's orbit is technically chaotic, with small changes in initial conditions causing large differences over millions of years. However, these unique properties of Pluto's orbit have been shown to effectively prevent chaos by maintaining stability over extremely long periods of time. Recent computer tests have helped us understand how the major planets Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special relationship with Pluto. While Pluto orbits the Sun twice, Neptune orbits the Sun 3 times. This connection helps keep Pluto's path stable, but Neptune isn't the only one who helps. Jupiter's gravity also plays a big role in keeping Pluto's orbit safe and stable, and Saturn helps a little. This test shows that Jupiter's gravity itself is strong enough to keep Pluto on a stable path for very long periods of time, even billions of years. This is how Neptune, Jupiter, and Saturn work together to keep Pluto safely navigating the universe without problems. This phenomenon is necessary to maintain order and predictability in the movement of space objects in the context of the universe. Without this mechanism, in the case of Pluto, especially when we talk about the possibility of a future collision with Neptune, it is really important to understand its orbit. It gives us a clearer picture of the dynamic nature of the solar system. Pluto's case shows us how even the most seemingly unstable orbits can reach equilibrium through the complex interplay of gravity and orbital dynamics. It also shows us the importance of continuously observing and studying these phenomena to better understand our place in the universe. As we explore the depths of space, we often encounter the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which describes the sensitive dependence of a celestial body's path on initial conditions, is clearly illustrated in the case of Pluto. This means that even small changes in the dwarf planet's position or velocity can significantly alter its long-term orbit. The use of computer simulations has proven invaluable in helping scientists figure out how Pluto moves through space. These simulations use complex mathematics to simulate the way Pluto and other cosmic bodies, such as Neptune, are attracted to each other. By changing small details in the simulations, astronomers can see how even small changes can make a big difference in where Pluto goes. In the late 1980s, these simulations showed something really interesting about Pluto's path. Despite the fact that Pluto has features like azimuth and latitude that keep it stable, its orbit is still very rough and unpredictable. Starting with small differences in Pluto's position or speed, its path can look very different a few years later. But despite all this chaos, Pluto's orbit remains stable for very long periods of time, billions of years. This means that Pluto's journey around the Sun, even if it seems chaotic at first, has some sort of order to it. Predicting cosmic events is a major challenge, especially when dealing with a chaotic orbit like Pluto's. Due to the inherent unpredictability of these systems, long-term predictions are often fraught with uncertainty. Numerical modeling provides a powerful tool for understanding and predicting the future trajectories of celestial bodies, but it also highlights the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they model. Small mistakes or oversimplifications can lead to very different results, making accurate predictions difficult. Furthermore, the chaotic nature of the orbits of bodies like Pluto reminds us of the constantly evolving and dynamic nature of the universe. Although we have made significant progress in understanding the universe, the case of Pluto reminds us that our knowledge of the universe is still limited. Understanding the gravitational influence of the giant planets orbiting Pluto can provide valuable information about the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching consequences as they affect the stability and trajectories of other bodies in the system. So why are leading astrophysicists only now raising concerns about the possibility of a collision between Pluto and Neptune, when all these complex forces are working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and leading figure in popularizing astronomy, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, best known for his role in reclassifying Pluto from a planet to a dwarf planet, offers insightful commentary on the evolutionary nature of celestial dynamics and the public's fascination with uncharted regions of space. Tyson's stance on the Pluto reclassification is rooted in the fact that our knowledge of our solar system is constantly expanding. He sees the reclassification not as a downgrade, but as a necessary adaptation to our growing understanding of the many celestial bodies orbiting the Sun. Tyson's approach to celestial dynamics is one of continual learning and adaptation. He sees the complexity of orbits like Pluto as a reminder of how much remains to be discovered in the universe. Conspiracy, the unique orbit of Pluto, and the potential future changes to its classification are the subject of lively debate in the astronomical community. Michio Kaku is an astrophysicist known for his ability to bridge the gap between the complex world of theoretical physics and the public's understanding of cosmic phenomena. Kaku's view on the possibility of a collision between Pluto and Neptune focuses on the larger picture of gravitational interactions in our solar system. He emphasizes that orbits are not fixed but change over time, influenced by a number of factors, including the gravity of the giant planets. Kaku uses this perspective to highlight the unpredictable nature of space, and that while current simulations assume stability, we cannot rule out future events that could upset the delicate balance due to unexpected gravitational interactions. Kaku's commentary goes beyond the technical details of Pluto's orbit. He sees the dwarf planet's path as a symbol of a larger dance of celestial dynamics, where small factors can produce profound changes in a body's trajectory on astronomical timescales. Kaku's insight highlights the need for continued research and observations to improve our understanding of these dynamic processes. The possibility that Pluto will eventually collide with Neptune is highly speculative, but it sparks a conversation about the importance of monitoring long-term orbital patterns. The small probability of such a collision forces us to reconsider the role of chaos theory in our understanding of celestial dynamics and in predicting the future trajectories of objects in the universe. The discovery of a possible collision between Pluto and Neptune is a stark reminder of the ongoing and dynamic nature of celestial dynamics. While current scientific understanding and numerical modeling suggest a low probability of a collision, the inherent unpredictability of chaotic systems underscores the need for continued observation and research. Tyson,